Okay, hi everyone. My name is Shea Garrison-Kimmel. I'm going to tell you today about the Elvis project, which is a suite of simulations that I've been working on with James Bullock and Mike Bolin-Colchin, whose names for some reason did not show up on that slide. In the background here you can see one of the simulations just sort of rotating around indefinitely. So I want to start by showing you this image from Via Lactea 2, which is, of course, one of the highest resolution zoom-in simulations ever run on the Milky Way-sized halo. To give you a sense of scale, the Milky Way is going to live here in this little tiny bit in the middle. Now this simulation and Aquarius and others like it have been and continue to be fantastic for studying galaxy formation. But thanks to upcoming telescopes like LSST, we're really moving towards a new era where we should zoom out on this picture and look at the larger scale. But of course, when you do that, you see another nearly identical halo nearby, this one hosting M31. Really, we should probably refocus to look at these two halos as a pair as a local group, right? So with that in mind, we decided to create the Elvis suite, which stands for Exploring the Local Volume in Simulations. The Elvis suite is made up of 44 dark matter-only halos in zoom-in simulations. 22 of them are in a paired configuration similar to the local group. The other 22 are mass-matched isolated analogs. It spans roughly the suggested parameter space for the local group. So for example, the individual virial masses vary between about 10 to the 12 and about 3 times 10 to the 12. We have enough resolution to reliably identify all the halos that we would expect to host the ultra-faint dwarf satellites, which means that within the virial radius we have about 15 million particles. And since we've taken pains to resolve the region outside the virial radius with high-resolution particles as well, we have up to 61 million such particles in our uncontaminated volume, which can be as large as about 43 cubic megaparsecs. Now here I'm just showing you visualization stills of all 11 of our pairs. I really just want to point out the diversity that we have here. So for example, here we have two pretty sizable ones that are very close together. To give you a sense of scale, sorry, all of these except for this top one, which is different, are 1.5 megaparsecs on a side. We also have, say, two smaller ones that are separated by a pretty sizable distance. We have an ongoing major merger here. So we just span, a lot of stuff is going on in this sample. Okay. So let's jump directly into results from the Elvis suite, starting with nearby halo counts. So I'm plotting here the number of halos with M peak bigger than a given M, where M peak is the largest virial mass that the halo has over its entire main branch history of the merger tree. I'm normalizing here by the virial mass of the host. Implied in red are the isolated halos. The mass function of the isolated halos implied in black are the same for the pairs here within our vir. The thick solid lines just indicate the average, which as you can see agrees perfectly even up to the high mass end, which is good news because otherwise Aquarius VL2 we would have to question them. However, when we look further out, when we look explicitly at field halos, here removing everything within our vir, we find approximately 80% more halos at a given M peak around the paired simulations than around the isolated ones. So from here on out, I'm going to go ahead and drop the isolated simulations because we know now that they'll agree in here and they'll disagree out here. Okay, so if we want to make a prediction, though, we need to predict an observable. So we can use abundance matching to predict the stellar mass function. So here I'm plotting what we get when we use the Baruzzi 2013 prescription. But interestingly, I'd like to point out here that in this regime, about 10 to the 5 to 10 to the 6 solar masses in stars, we strongly overpredict the number of galaxies. So we thought, well, that's kind of interesting. We're not really sure why that is, but we decided to try and fix it first of all. Now at the faint end, the M star M halo, the abundance matching relation, is approximately a power law. The Baruzzi 2013 prescription used the power law from the Baldry 2008 paper, which used SDSS. If we do nothing to the abundance matching prescription except modify that faint M power law to be that suggested by the Baldry 2012 paper, which used the gamma survey, then we get much better agreement in this regime. And we then predict about 300 galaxies with M star bigger than about 10 to the 3 solar masses within 300 kiloparsecs of either the Milky Way or M31. Now we can then use that same abundance matching prescription and look further out, because remember, we've taken pains to be uncontaminated, even out to 1.2 megaparsecs. And if we do this, then we predict about 1,000 galaxies within this sort of oblong region that's 1.2 megaparsecs of either halo center. Now this here, this fall off here, is really just incompleteness. And Zeus and Hera is just one specific pair that we highlight because it happens to agree quite well. Okay, so the next result I want to talk to you about is backsplash halos, or backsplash galaxies, which we're going to define strictly as any halo that has passed within the virial radius of one or the other or both of the hosts at any point, basically. So we're not saying it has to be within R vir over 2 or R vir over 3, just R vir. So there are 3 samples plotted here. The paired and the isolated are pretty obvious. The shared volume sample counts only halos that meet the radial cut for both hosts simultaneously. So that applies to the pairs, obviously. Interestingly, they tend to generally agree. But what I really want to point out is that even out to 2 to 2.5 R vir, you have about 20% of the halos out there have at some point or another passed within R vir of the host. And if you look all the way within about 1 to 1.5 R vir, it's something like 75% of those halos have been within R vir in the past. Now we're going to do the ultra simple thing and say that all of these galaxies that have ever been within R vir have no gas today. They've had all their gas removed via via ram pressure stripping. And then let's just see what that gives us. Well, it turns out that it gives us this H1 mass function that actually agrees quite well with the observed H1 mass function, again, up to the incompleteness limit. Interestingly, though, we only predict about 100 missing gas-rich objects around the local group, around the Milky Way and M31. Okay, so we can then compare all these gas-rich objects to observations. So here, what I'm plotting on the left is in diamonds are the gas-rich objects around one of our halos, in this case Hera. And in circles are the alfalfa ultra-high or ultra-compact high-velocity clouds, which they think might be extragalactic mini-halos. Now mostly I want to draw your attention to this set up here of ultra-compact HVCs that are moving away from us very quickly, which correspond to this peak in the velocity histogram, the radial velocity histogram, which are just totally incompatible with the nearby dwarfs. So as sort of a 0th order prediction, we think that these guys are probably not outside the Milky Way. They might be something within the Milky Way, or they might possibly be something a lot further away that's part of the Hubble flow still. Although that would bring up some issues with the mass. Okay, so everything I've shown you thus far is going to be, and a whole lot more actually, our results are going to be in the first Elvis paper, which will hopefully be out within a month or so. I want to spend the rest of my 3 minutes talking about something that is a little more preliminary still, and deals with too big to fail. So Oliver told you about that a little bit, but to remind you, it's an issue with the internal structure of subhalos, basically. So to start, we want to compare the paired and isolated samples to see if there's a difference between them, and if there is, why, and if not, then we can go ahead and combine them. So plotted here is the Rmax versus Vmax for all the subhalos in Elvis. In red, again, are the isolated, and in black are the pairs. Vmax is, of course, the maximum circular velocity, and Rmax is the radius at which Vmax occurs. The lines are the fits to the two populations, which, as you can see, agree to entirely within the errors. So that means that we can go ahead and combine these two samples to get better statistics. Now, based only on the Rmax and Vmax values plotted here, we can extrapolate an NFW profile. Or if we use a given shape parameter, we can extrapolate an ionostar profile. So plotted here then, hope you can see that, good. Plotted here are the circular velocity profiles that we get, assuming an NFW profile, around one of our halos. Now, the standard definition of too big to fail would say that this guy, this solid black line, which lies above all of the Milky Way dwarfs, which are what these points are, is a too big to fail halo. It's a massive failure. But if you look at this and you say that there's only one massive failure in this system, then you're kind of lying to yourself. Because all three of these red lines can only fit in Draco. Or sorry, Draco can only fit in them. No other galaxies can fit in those red lines. So if we say there's one massive failure in this halo, then we're trying to put one Draco, which is a very rare object, into 3 subhalos, which is kind of unfair. Really, what we should do is say that one of these works and goes through Draco, and the other 2 are still massive failures. And we can then play that same game with the other 3 dwarfs that are significantly denser than the remaining 5. And then we end up getting a plot that looks something like this, where I've highlighted those 4 in red. And you can see that there are 4 lines going through those that are dotted, and the rest remain solid because they're massive failures. So that gives us 11 failures in this halo. Now I'm not going to show you 44 of these plots for 3 different profiles. Instead, I'm just going to show you the cumulative number of unaccounted for subhalos, so the number of massive failures in each host for 3 different profiles, an overdense, an nosto, an underdense nosto, and an NFW. What I really want to point out here is that even in the most extreme case where we have a very underdense nosto profile, we still have at least one massive failure, even in our best case dwarf, or sorry, our best case host. And our median is something like 15 to 25, depending on what profile you assume. So basically, it seems unlikely that the Milky Way is just an outlier halo with no massive failures. OK, so to summarize some of the Elvis results, in terms of halo counts, we found the paired and isolated samples agree, but we have a lot more outside our VIR. Abundance matching, we found that we need a flatter faint end slope, and we then predict about 1,000 galaxies near the Milky Way. We find about 100 unfound gas-rich halos around the Milky Way in M31, which tend to be inflowing, unsurprisingly. And we also find that requiring that each dense galaxy lives in only one subhalo results in about 15 to 25 failures per host. I'm going to leave up just some ongoing Elvis projects and tell you that we will be releasing the data publicly soon. But if you want early access to it, please contact us, and we'll happily work with you to share it. Thank you.
Are the unfound H1 galaxies findable, or are they lost in the Milky Way?
We haven't looked at that, actually. So to give you an idea, there it is. So we've rotated this image such that M31 is actually where M31 is. And you can see most of them do not really lie. So this is in LB coordinates. Most of them do not really lie along the disk, but some of them, it's just going to be luck, basically.
You're worried about space with the velocity.
Yeah. So that's something that we haven't really thought about that. As you can see, alfalfa is this dip here because they've explicitly excluded things that are close to 0. And we don't. We have a lot of stuff there. So yeah, we might not be able to find those.
In your definition of massive failures,
Mm-hmm.
what are you calling too big to fail? I mean, what are you calling too big?
We're calling too big anything. So we select these 4 somewhat arbitrarily, but they are outliers in the density, the bands, as you've probably seen.
Things that are denser than that.
It's things that are unaccounted for that are denser than these 4.
Okay. But we know there's a lot of scatter within the Milky Way in the galaxy formation efficiency.
Right.
And just because all of your halos have some denser objects that haven't formed galaxies, right? Some of them only have a few.
So
we know the Milky Way is right. The Milky Way itself isn't, on the low end of other galaxies.
On the low end in what sense?
Well, you're only comparing these to the Milky Way itself, right? To the Milky Way dwarfs. Handful, right?
Yes. You're saying why? How do we know the Milky Way dwarfs are not fewer than we expect?
Given that we already know there's a lot of stochasticity in their efficiency.
So I didn't put it on here, but the M31 results that we have don't really differ. Evan Kirby has a galaxy in the field that looks exactly like the Milky Ways or the Milky Way dwarfs that we've seen here. It could be, and so that's sort of what this definition looks at, is just everything denser than any of the Milky Way dwarfs. And if we do this, we get about 10% of our galaxy, or of our hosts, have no massive failures. So maybe if it's something like that, and we just haven't found another 4 Dracos and another 3 Ursa Minors and so on, then it's maybe not too bad.
How does the presence of the Magellan cloud affect those kind of statistics?
So we haven't looked at that explicitly. That is, we did make an effort to include some halos with LMCs in our sample, but we haven't yet gone through and said those that have LMCs, are you more likely to have massive failures and so on and so forth. We haven't done that yet.
Can you borrow your adapter?
Yes, although it's actually Kyle Stewart's.
Okay, great. We'll just leave it at that. We can use it.
Okay, one short question. Well, yeah.
Yeah, just do you have a plot where you only have the massive failures that are massive failures and not missing failures?
Yes. Although, do you want me to plug back in and?
We're running out of time.
The median in that case is, here we go. Whoops. So this is that plot. So our median, again, it depends strongly in this case on which profile you use. But it's anywhere, we have 10% in an extremely underdense anostar profile. 10% of them have no failures. If you assume an NFW, 1 of them out of 44 has no failures. If you assume an overdense, then none of them have no failures, and your median is something like 12.
If you did shift the Milky Way mass down to 10%,
We don't know because we have picked only things bigger than 10 to the 12, as suggested very strongly by the larger scale mass measurements like the timing argument and